Today we're going to talk about oscilloscopes. We've got a PC-based oscilloscope here. Now you might have seen older style oscilloscopes, which are screens, little digital screens or CRT screens that you would see balanced on a workbench in an electronics workshop somewhere like this. PC-based oscilloscopes are quite accessible and they give us loads of options for what to do. So in this video I'm going to talk you through what a PC-based oscilloscope is, how it works, how you would use it, and we're going to use one to make some compression measurements on this engine. We're going to do what's called a relative compression test. But first of all, let's talk about an oscilloscope and how exactly it works and what it is. So essentially, we have here our oscilloscope, and it's a box which plugs in via a USB cable into a computer, a PC of some sort, or a Mac. And the box has 4 inputs. So on our box here we have 4 inputs. Each of those inputs can measure a voltage. So it's called a 4-channel oscilloscope. You'll find a 2-channel oscilloscope or 1 channel. Each channel is measuring voltage. So you can think of each channel like a voltmeter. We have a voltmeter here. And this is a fairly good quality industry standard voltmeter. And we use a voltmeter to measure volts. So if I put this voltmeter onto the battery here in an attempt to hold this in a way that you can show and also put it on the battery, let's put it there like this. Hopefully you can see the screen. We put this onto the battery. Where are we? This is positive. This is negative. We should see 12 volts. So we get 12.75 volts on there. And that's our measurement. Now if I move one of these around, you'll see that the voltage will probably vary. I mean, it doesn't seem to be. But any variance in the voltage, you would see this number update, maybe once a second, twice a second, we can see this. So if we have a voltage which is changing, if you imagine a voltage which is going up over time, for example, it's slowly increasing over 2 seconds, we would see this screen update and we might see, for example, 0 volts, 2 volts, 7 volts, 12 volts. But we don't really get a feel for what's happening over time, and if something's changing more than every half second when this display updates, we won't see. We'll simply see the voltage at the point in time when it's displayed on this screen. Now an oscilloscope takes a voltage, measures the voltage just like this, but it measures it thousands of times a second, and it then plots that voltage onto the screen. So what we can see is I have the oscilloscope connected via what's called a BNC connector. So we just plug in, and from that lead we get 2 connections, 2 wires that come out, one for ground, one for signal. So we have a signal wire here and a ground, and just exactly the same as a voltmeter, these are our 2 leads. So if we connect the negative or the ground to the negative of the battery and our signal or positive lead to the positive terminal, you can see that we're measuring this voltage, and we have on the left a scale. So 0 is around here, and we can read off the scale that our voltage that we're measuring here is 12 volts. And it's just a flat line. So on the vertical scale is the voltage that's being measured. On the horizontal scale, across the screen here is time. Now in our case, nothing's happening because we have just a flat voltage, 12 volts DC, coming straight out of our battery here. The benefits of an oscilloscope become more clear if we have something that's generating a voltage that's varying over time. So let's look at a battery charger which produces kind of an interesting waveform as it tries to detect a battery that's attached to it. We have a battery charger here. Now a battery charger sends out a signal to detect whether there's a battery attached to the charger, whether it should send out charge or not. So if we take a look at what's coming through here, we put our voltmeter on here, we'll find a voltage. What do we have? Okay, we've got minus 0.76 volts coming off, and it's fairly stable. So that's a little voltage that the charger's sending out to see, do we have a battery attached? Now, if we connect our oscilloscope across those same leads, we see something, hopefully, a little more interesting. We connect that to the ground, this one to the positive, and now we see a waveform. And we can zoom in a little bit, get to a more comfortable resolution, say 2 volts. Now there we have a waveform over time. And what we can see is that the voltage is moving from 0.2 volts down to 1 volt over time. So our maximum current or our maximum voltage is -1 volt. Our maximum is 0.2 volts. What we were reading on the multimeter, on the voltmeter, was 0.76, minus 0.76. And actually, that's kind of just an average of what we're seeing on the screen here. So that's what an oscilloscope lets us do. It's one of the benefits of an oscilloscope, is to see in more detail what are we actually getting in terms of voltage over time. The other huge advantage of an oscilloscope is that although it measures voltage, all our inputs here are measuring voltage. So we can feed it any voltage, up to 100 volts or so, and it's going to measure that over time. Wonderful. The key to an oscilloscope, the thing that makes it super, super useful, is that you can get sensors or transducers which convert other things into a voltage that this can read and store and record. So we can, for example, we can record current over time. We have a sensor, a current sensor, which clamps around a wire, measures the current going through that wire, and the sensor itself converts that into a voltage which the oscilloscope puts onto the screen for us. Okay, that's useful. We can also measure pressure over time. So there's a sensor which will measure the pressure inside a cylinder or in a fuel injection system, or anywhere basically that you have pressure. It will take the pressure reading of that system, convert it to a voltage, and put it on our screen here across time. We can also measure temperature, we could measure light levels, we can measure vibration, sound, all these things over time plotted up on a screen. And that's super useful when it comes to seeing what's actually happening somewhere. What we're going to do on this next test is we're going to clamp a current meter around the supply cable for the starter motor, and we're going to see how much current the starter draws over time. And the resolution on this, the resolution being how often it takes a measurement, is extremely high, a high resolution device. So every thousandth of a second or so, or even more, it will take a reading for the current flowing through this wire. So we're really going to see in detail, almost in slow motion, what exactly is happening when the starter takes power. One of the reasons an oscilloscope is super useful is we're not just interested in whether things are on or off, or what their voltage is at a particular point in time. We're more interested in when are things on or off, particularly when we come to looking at sensors and things like that. It's the actual timing that's the really important part of what's happening. And particularly with multiple inputs, we can look at how things are reacting over time compared to each other. So for example, we could look at the pressure in a cylinder compared to the ignition circuit. We could look at the starter motor turning over and at the same time look at the voltage in the battery, for example. We could measure the drain, the draw away of a vehicle. Say you have a vehicle which you're leaving overnight and the battery is drained in the morning. We could attach an oscilloscope and actually leave everything on battery, leave it overnight, and in the morning look at a graph of the battery voltage and the current being drawn over time, and maybe get some clues as to what is it that's draining this battery. So sometimes we're looking at a really, really tiny time scale, looking at things over milliseconds or microseconds. Other times we might be looking for a 24-hour period or a 1-hour drive on the highway, something like this. So there's lots of different ways that an oscilloscope can be used. Let's get this stuff taken to pieces. Let me clear some space here. We'll hook up our current clamp and we'll run what's called a relative compression test. We already did a traditional compression test on this engine. So we used a compression gauge, and the way this works is that we whip out all of the spark plugs, insert this into the spark plug hole, screw it down, crank over the engine, and this gauge will tell us the maximum pressure that was hit on the compression stroke in each of these cylinders. We then compare those numbers to, firstly, the pressure that should be reached in the cylinder, compression figure that the manufacturer has given us. So for example, the gauge reads 180 and the manufacturer specifies 180 psi. We know that that cylinder has good compression. But what we're looking for as well is consistency across all of the cylinders. We're looking for numbers which are more or less the same across these cylinders, because what we want to see is whether one cylinder is more worn than the rest. That's going to reveal faults with the head or with the valve gear, with the piston rings and so on. So a relative compression test, which is what we're about to do now, has some big advantages over this traditional compression test. A relative compression test using a scope, we can do very quickly with the engine in the car. We simply disable the ignition system, hook up the clamp, crank the engine over, and we're going to have a very quick idea of the relative compression inside each of these cylinders. But it won't tell us the actual compression number. So we won't get a number from a relative compression test that we can compare to a manufacturer's figures. We don't get this PSI number. What we do see, and what we will get, is a nice graph which will show us the current being drawn to crank over each of these cylinders, to compress each of these cylinders. And we can compare the peaks on that graph and see relatively how consistent are these cylinders in terms of compression. So what we will do is use a current clamp. Now this is a picoscope, top end scope, and it comes with two different clamps, two different current clamps. We've got the low amp clamp here, which goes up to 60 amps. That's not enough for us. We are expecting, the other thing with using a scope is you need to know roughly what you're expecting to see, what number you're expecting. For us, we're looking at current through this wire. We know that's going to be anything from 100 amps up to 600, 700 amps on a spike at the very start. So we'll use the high amp clamp, which goes up to 2000 amps. And what we do with this clamp, we just clamp that across our supply wire. Note that, in fact, that's the wrong way, because we have an arrow which indicates the direction the current is flowing along this wire, and we want the arrow to point along the direction of current flow. It's no problem if it's the wrong way round, but the graph on the screen would be inverted, so we'd be looking at negative numbers, and it's just easier for our minds to work with positive numbers. So we connect our clamp, which converts the reading. It reads the basically it reads the current flowing through this wire. It has a sort of Hall effect sensor inside, and that detects the magnetic field that's generated by the current. So we connect that to our scope, and the sensor here will convert the reading in amps into a voltage which our scope can then display on the screen. So we connect that to the A channel. So we have 4 channels on this scope. That's into A. On C here we have our just probes basically reading voltage. And what I think we'll do is we'll just connect these other C channel to the battery. And that way we can see 2 things at once. If I can untangle this spaghetti chaos. We'll just clip these onto the battery. We've got the battery down here. Can I reach? Okay, so with our battery connected, we should be able to see the battery voltage here. And let's change the range. So on the green side, on our green scale here on the left, in the green corner, we have voltage. Let's change the scale here. So the moment we want to see. Again, this is about understanding what it is that you're expecting to see. So we're expecting to see around 12 volts from the battery. So we're going to change our scale to be plus or minus 20 volts. So we know we'd see 12 volts in there. And yes, we do. We see here on the left, we have a nice flat line across the screen of 12 volts. And what we can do is we can move this up or down, and you can see the scale is moving up and down the screen, and our line is actually moving. So let's just stick that on a nice grid line so that we can see if that moves. 12.75 volts is what's coming off the battery. Now let's get our current clamp working. Although, before we do that, we need to install the spark plugs, because on a relative compression test, you need your spark plugs installed, and all you need to do is disable the ignition system so that the engine doesn't fire up, and you can take your compression test. Now, if you think back to the video that we just did on compression testing, we found that we had high compression in one cylinder and slightly low compression in number 3 cylinder. So I'm interested to see how this shows up on the graph as we run this relative compression test. Do we see those differences in compression or not? We're going to find out. Stay tuned. There we go. Spark plugs are installed. Now, without spark plugs, we would have had no compression at all, so we would have seen almost nothing interesting. However, now we will. So, our current clamp is installed, the arrow's facing the right direction, we're connected to channel A on the scope. Let's turn on channel A. Now, this is an interesting thing with this scope, is that there's a library of input scopes or sensors. which you can choose from, and it does the conversion from millivolts, which is what this system is reading, into amps, which is what we're actually looking to measure. If it didn't have that function, then what we would read on the screen here would be, for example, 200 millivolts, and we would have to calculate that. I don't know the exact number. In fact, it tells us on the clamp here. It tells us that in 200 amp range, 10 millivolts equals 1 amp. So if we saw, for example, on the screen 200 millivolts, we'd have to do the maths to say 200 millivolts divided by 10 gives us 20 amps. That's what the current's reading. Now this software just does that conversion for us automatically. So we can read on the scale directly in amps rather than have to read millivolts and do that calculation ourselves. So if we choose from the library here, we're looking for a 2000 amp clamp, which is down here. And we're going to run, we've got 2 modes to choose from. You can see here we've got 200 amp mode and 2000 amp mode. 200 amps is not enough for this starter motor, so let's go with 2000 amp mode. And it automatically, or it should have, we change this to auto, now we'll see that this will appear on the screen. So there we go. We now have, we've moved across so that on the right, in the right corner, we have voltage in green. In the blue corner on the left, we have ampage, which is reading 0 and it's a little fuzzy. That's almost certainly because I haven't turned on the amp clamp. So we need to turn this on, slide this up to 2000 amps, and we'll hit 0, and it's going to 0 our clamp. So there we go. Now if you look at the, I'm attached to my engine here, just a moment. If we look at the scale here, you can see that we're on 0 and there's a fluctuation of, you know, around 1 amp in theory. That's just the magnetic noise that this clamp is detecting. We need this scale. At the moment we're set to auto. You see here, this is our vertical scale. So let's set that to more like what we're actually expecting to see. And we're expecting, I think, to see a steady current of 100 amps, something around that mark while it's cranking, and it's going to spike up to anything, maybe 1000 amps, possibly just for a moment as this gets going. I know this starter is, I think, a 400 amp starter, something like this. So there we go. Now we can see down here, we're on 0. This scale has changed to kiloamps, how would you even pronounce that? Anyway, it's in thousands of an amp. So, thousands of amps. Let's move this back up so we can see this on the screen. And we can see a nice separation in our circuits. The other thing we need to think about is time, and time is represented in the width. So at the moment we're at 10 milliseconds per division. So every one of these divisions here is 10 milliseconds, 10,000th of a second. We have, how many divisions do we have? We have 10 divisions, so we're covering 100 milliseconds per screen, so we'd need 10 screens for 1 second. That is just too much for what we need. If you think that we're going to be turning over this engine, we're looking at, you know, the amount of time to crank all 4 of these cylinders. If you even think about how an engine sounds when you crank it, we're probably looking to measure for 2 seconds, I would say. Maybe 1 second per screen would be good for us. You know, if you turn the key in a car and you think it goes, that's probably a second, maybe 2 seconds. So that's the sort of range that we're looking at. We're certainly not looking at millionths of a second here. We're closer to seeing on one screen, and this system will record multiple screens, but we really want to see on one screen what exactly it is that we're measuring. So what we'll do is I think we'll choose per division, we'll choose 500 milliseconds per division. That's going to give us 5 seconds right across the screen. I think that's going to be just about right for us. And you can see that this number is moving across the screen now, because before we were in such a small time scale that it really didn't update the screen. But now you can see as 5 seconds goes by, these lines are moving across the screen. This is a real-time measurement. This is the current situation, live and direct from the battery and the engine. So let's just turn this over and see what happens here. We're ready? We hit the ignition, off we go. Aha! You see this? This is our current. Now, because we're on this constant mode, this constant running, this constant refresh on the screen, our reading just disappears. We can hit stop, and I think we could go back some screens. If we can get this to stop, we may be able to go back. No, we can't, because I wasn't recording. What we want to do here is we want to change. Down here we've got a setup of modes, and we want to be in single mode rather than repeat mode or auto mode. We're going to set this to single mode, and what that's going to do for us is it's going to take one screen full, and then it's going to keep that on the screen, which is what we want to see. So if I stop this now, stop capturing, we also want to set what's called a trigger. So where is our trigger? Here. We have here a yellow dot, and this yellow dot is going to start the measurement when the current passes this. So we want to change the channel for this A, okay, and now we have our trigger. So a trigger is basically saying to this system, when the measurement that we're looking at, and in our case we're looking at current, when the current triggers this, then start to record and record one screen full from there. So that's what we want to see. Once the current spikes up beyond this, which is at 140 amps, that's too high. Let's bring that down. Let's bring that down to, I don't know, 10 amps, something like that. As soon as the current goes past this 10 amps on the way up, and we know it's on the way up because we've got two options down here for when to trigger it, we'll leave it as on the way up, we'll record a whole screen full. So now, when we hit play, you can see we've stopped right here at the trigger. And as soon as we run the ignition, it's going to trigger this, it's going to record us a screen full, and we can come back and look at it in detail. So let's do that now. There we go. Hits the end of the screen. Okay. And it stops. And we can now look at our information. So what can we see? This is our current, spikes up to 500 amps on the initial crank, where it has to overcome the inertia of the flywheel, the crankshaft, and all the inner workings of the engine. Then we settle down to a cranking figure, which is, let's say an average 135 amps, something like that, 130 amps. You can see immediately we get a lot of information out here. At the same time, the battery voltage drops. So if we look across to the green scale, our voltage scale, what you can see is that in that initial spike of current where we really pulled the juice out of the battery to get the engine turning over, the voltage in the battery supplying that current was dropped down to 8.8 volts or thereabouts, and it then came back up, and the cranking voltage of the battery was around 10 volts, 10.5 volts, something like that, until we finished cranking. Each of these spikes down here, let's zoom in a little bit, each of these spikes is a compression stroke. What's happening is the starter motor draws the amount of current that it needs to do the work. So the harder the starter is working, the more current it's pulling out of the battery. It's harder to push the cylinder up on the compression stroke. That's when the motor's really doing the work to drive the piston up and to compress that gas mixture. So on the compression strokes, we should see, and we do see, that the current being drawn by the motor rises. And the harder it is to compress that piston, i.e. the more gas-tight seal we have, the higher the current draw is going to be. So we can use this current draw figure as a proxy for the amount of compression being generated in the piston. If we had worn piston rings or something like that, it would be much easier for the starter motor to drive that piston up and to create the compression. So what we're looking at with these peaks is a consistency. How even are these peaks as we go across? And they're pretty even. This is quite a nice compression figure. So we've got 4 cylinders. The first crank, the first compression stroke took a bit more power. No wonder, things kind of slow. The oil's just getting up to pressure in there. Then from there on, we're more or less even. So we don't know what numbers these are. So let's say 1, 2, 3, 4, 1, 2. Something happened here. And that's interesting. Something's happened here and there was no compression, or more likely, and from hearing the way this sounded when we cranked it over, I suspect the starter motor stopped for a second. Something happened there, and maybe it just lost some current, maybe the solenoid tripped slightly. Something occurred here, and then we continued on. Now, if we had a fault with this engine, we may have just got a real clue as to what that fault was. We don't have a fault that we're aware of, so we just assume that there's some sort of mistake there. But that is the results of a relative compression test. We don't know what the compression is of this engine, but what we do know is that all 4 cylinders are more or less the same, and that may be all that we need to know, particularly if you were looking for a misfire. If you had a misfire on 1 or 2 cylinders in this engine, this graph would tell us that you can probably ignore compression as the cause of that misfire, because we know that our cylinders are more or less equally worn or unworn, as the case may be. Now, the next thing that we'll do is we will use a pressure transducer, which can actually tell us the exact numbers. It will measure the pressure inside each of these cylinders. Now, again, just like a traditional compression gauge tells us the maximum pressure that was hit in that cylinder. The pressure transducer will tell us the change in pressure over time. It's going to display on the screen a nice graph of pressure over time, which could be a really interesting number. This relative compression test is a go-to test. If you've got a scope and you need to test the compression of an engine, this is the way to go, because you just simply need to clip on your clamp, your current clamp, and disable the ignition system, and there's your relative compression test. If we're going to get out the pressure transducer, then we need to remove the spark plugs and do that kind of groundwork that's required, just as with a traditional compression gauge. So it's a slower test, but it gives us some really interesting information, so we're going to do that now. Okay, what we have here is a pressure transducer. A transducer is something that converts one form of energy into another form. So in our case, we're converting the pressure, kinetic energy, whatever you want to call it, we're converting the pressure there into an electrical voltage, something like that. So that's a transducer. Now, this transducer here has three modes. It has, if we read on the back here, we've got mode 1, which gives us a range from -15 to 500 psi. Mode 2 gives a much higher resolution, a lower range but greater detail, and we can go down to measuring plus or minus 5 psi. So for us on this, we are looking really at, again, you've got to know what you're expecting. We're expecting 180 psi, so the first range is the one that we're looking for, from -15 to 500 psi. That's going to give us a lot of sealing room above and below, although it wouldn't be sealing room below. A lot of sealing room and basement space. So let's pull off our cable, get this thing plugged in. Now these, okay, let's try and plug this into the right thing, shall we, Alex? All right, let's do that. So this transducer comes with all sorts of accessories so that you can fit into the fuel system. You can measure all sorts of different things. We've got different spark plug hole adapters. This is what we need. This just clips onto here. If we can get that on there, retract that. There we go. Just like a compressor hose fitting. There we go. We're fitted in there. I don't know if it needs a battery. I haven't put one in. Well, it's turned on. There we go. So we're on. We choose our range, which is flicking up. Okay, we're on range 1. We don't need to use zoom. So let's connect this into our first. Let's remove the spark plug. Let's remove the spark plug, shall we? So we need to remove all 4 spark plugs. We do need to remove all 4. Let's do that. All right. Out with the plugs. Out with the plugs. You'll remember when I talked about the clamp meter and we looked at that, I said it converted, I think it was 20 millivolts? No, 10 millivolts per amp. So that was what was coming out of there. If we looked at this, I'm sure it would tell us on the back. Yeah, it tells us 1 volt per 100 psi. Is what we're looking for from this. So every one of these sensors that connects to the scope is giving out a voltage, and on the sensor it tells you what the voltage that will result from the input is. So we're looking at pressure. This tells us that for every 100 psi that it's measuring, it's putting out 1 volt. So if we were measuring this on here and we saw in volts, 2 volts, we know it's 200 psi. But again, because this system automatically convert sensors. We're going to choose on the drop down the sensor that we're using is going to convert it for us, and on the scale we're going to see PSI. Hose pipe. I'll just fish out these plugs with a hose pipe. It's amazing what little tools are invaluable in the garage. This hose pipe, something like this. Cable clips, always essential. Right, we're on a spark plug free engine. Let's temp this again. So we'll screw our gauge into the number 1 cylinder. Oh, this is nice. Because it has this, I don't know what you call this, quick release coupling, something like this. We can actually screw this down much more easily than this gauge, which you have to turn the whole gauge and ballerina the whole thing around. Anyway, let's get this screwed down. There's a long thread on this. There we go. We're bottomed out there. Okay, we're turned on. We're on range 1. Oh, it's leaning. Let's bring it this way. I don't want this to disappear into the valve gear and get chewed up. Be in big trouble then. That looks okay for now. Should have the cam cover on this engine. I haven't put it on because we haven't talked about the cam cover yet. So, let's connect ourselves up. Where are we? I've lost the end of my cable. Yeah, you've got a good long cable on this. Right, we're going into channel B in red. So I'm going to leave the other 2 channels connected because we've got a 4-channel oscilloscope. We may as well use all 4 channels. I'm kind of tempted to connect the 4th one just for giggles. So we've still got the same settings as we had before. Everything's still connected as before. Let's enable channel B. So if we choose in B, we choose our probe, sensor, transducer. Do I know the difference? Not really. We are looking for a WPS 500X in range 1. That is our pressure sensor. So what we have is, in the blue corner on the left, we have current in amps. In the green corner, also on the left, we have voltage on the battery, which is 12 volts, and it's going to dip a little bit. Wonderful. Over on the right, we have our pressure from the pressure transducer. Now, the scale is in volts, and 1 volt is 100 psi. So we're expecting 180 psi or thereabouts. So we're expecting to see on here 1.8 volts as our peak. And down here is our 0 line. So for the moment, we're expecting to see this red line, which I know is not super visible. We're expecting to see this red line spike up on the compression stroke for the number 1 cylinder. Let's crank this baby and see what happens. Try not to lose my pressure in the workings of it. There we go. Let's see what we've got. So, okay, interesting. It looks like it's worked out quite nicely. What we've got, let's look at our 3 lines. We have the current in amps going into our starter motor. And interestingly, because we've removed all 4 spark plugs, we only have now 1 peak on the amp. So before this, we were seeing a peak for every cylinder. But because we've removed the spark plugs, the other 3 cylinders, they don't have any compression. So the starter motor's not doing that hard work to create the compression. So we no longer see those peaks. So now we only see the 1 peak, which is the peak for cylinder 1, where we have our pressure gauge installed. So that's interesting straight off. Now we have our pressure in there as well. What we can see is our pressure is actually going over the 2 volt scale that we're working on here. We're actually going higher than 2 volts, which means that we're over 200 psi, which is not surprising because if you saw the video before this, we actually measured, and this number 1 cylinder is producing higher compression, quite considerably higher compression than is the specs for this engine. There's some sort of issue there that we need to dive into, and it's confirmed by this test. What we can see is the pressure rises up. This is our compression stroke, and there we go. We have a steady, relatively even, although somewhat falling compression. I wondered if we crank this again, would we see? You see that we've come down here, we're just below 2 volts, just under 200 psi. Let's crank again and see if we are falling. I have to hit space and we set this up for a trigger. We still have our trigger, off we go. Okay, so it's fairly consistent. That's interesting. We caught this just at the tail end of a compression stroke, and you can see we created almost all the compression, and then that compression's just leaked away over the period of half a second. It takes half a second for us to lose 60 psi from the cylinder there. I think this gives you an idea not only how to do a relative compression test. Are you going to have a pressure transducer in your kit in the garage? Probably not, let's be honest. It's quite expensive specialized kit, but it does give you the idea of what's happening in a pro garage, what are some real cutting edge diagnostic techniques, and also hopefully a deeper understanding of the starter motor, compression in cylinders, and that sort of thing. But we'll be using this scope for a load of other stuff all the way through this series when we get into sensors, when we're looking at sensors, engine computers, engine management systems, other motors, actuators, anything like that will be on the scope because it makes sense. And hopefully when you look at this now, you will understand what you're looking at on a scope reading. I think as cars evolve, I mean, they're already very electronic, but this is really the sort of tool that will be standard practice in 5-6 years. You'll be working on this all the time. So a little instruction for you there. Maybe it was a little unstructured, but I think you've got the idea of what an oscilloscope does and what we can use it to do.